Hello, everyone. When it's my turn, everyone go home. I don't know, maybe go to see the city. I hope they enjoy, and I hope you enjoy your lunch and you will enjoy my presentation. It's not completely a future telling, and I'm not a gypsy to tell you the real future of the wireless technology. But based on the technology, there is possibility that can happen in the near and far future. So it's not accurate, but it's possible. Let's say it would be possible. To ensure that we are at the same page, I just prepare some basic of wireless technology, and I will tell you briefly because I had many presentation about them, and I don't want to bothering you with them. But we will need that because we want to make sure that we are reading the same page and we prepare to understand when we make any changes, what will happen to the speed and things around. So part of my presentation will be about the current technology and upcoming technologies that you will see in the next few years. So let's start together. Most of us think that data rate's coming from this bird. So when we're talking about 400 megabit per second, we just imagine this bird and we wait for data rate coming from the air. But there is a long story behind every number that you see on your router. And one of the best formula that you can, it's simplified. It's simplified to public understand, but it's so simple. You can use it even if you have a licensed band radio or anything similar. You can use this formula. You can add number, and you can have the result and anticipate your data rate that the radio will give to you. First of all, to understand that formula, we start from the channel width that you are familiar with. The channel width is the width of the channel that you are using. Mostly in the past a few years, we use 20 megahertz channels. So when we use one single channel, like a 5180, it means we are using 10 megahertz upper and 10 megahertz lower. If we look closer to that channel, we will see it's not flat. We will see there bump there. So the system can use that for data transfer. If we look very closer, we will see their difference from each other, and each one can means, depends on the modulation that we use, the number of beats. So if we use wider channel widths, we can have higher data rates. And that's why at AC standard, you can have 80 megahertz or 160 megahertz channels. It gives you better performance and give you double or 4 more speed compared to older technology, just because of that more width of channel that you are using. So that's a good idea to have a bigger channel. But we have an enemy to use that, and that's your regulatory. They don't allow you to use wide channel or 1 gigahertz of channel, because we should be a good neighbor to enjoy our neighborhood And if we use 1 gigahertz, we are not a good neighbor at all, believe me, and your neighbors cannot use that frequency. So we have limitations. The biggest limitation for using higher channel is disturbing others, and we don't have any more channels. So it seems the 160 megahertz is a very high end and very high edge of the 5 gigahertz band. We cannot expect more and bigger channels at this range of frequency. Another thing that involved in the throughput is our modulation. So to understand very basic of the modulation, what we are doing is converting 0 or 1 to some analog symbol. It could be ah, so I can tell you is 1, ah is 0, and I can start transmission. Okay? I do modulation, it's this much symbol, and depends on what kind of technology and what kind of modulation, I can have more symbols, just like oh, ah, ooh, or whatever it is. So if I use more symbols, a, I, O, I can transmit more data. That's so simple. So that's where the QAM goes to play, and with 16 QAM, we can transmit 16 symbols. Okay, each symbols can means one of these. This symbol can means 4 bits. If we use bigger QAMs, we can transmit more bits with only 1 symbols. Okay? If we use 64 QAM, each symbol can means 6 bits. If we use 256 QAM, each bits can means 8 bits, and it can go up to whatever the technology allows us. Okay? For AC standard, the 256 QAM come to play, and it gives us 33% more throughput. So that's a good news. We should look forward to what will be next. There's one more parameter that's playing a big role in our data rates, and it's forward error correction. Just imagine you're watching a video from a digital source like satellite or any kind of digital transmitter, and one error happened in a very lovely moment of your movie that you really like. You cannot use your phone and call the broadcast channel to send that video again to you. It's impossible because it's a broadcasting. So before you call them, they should think how they can improve your reliability to don't have any phone call from you any moment. That's one of the methods that send you backup. When we talk about FEC, forward error correction, it means instead of 1 bit, I'm going to send you 3 bits. So more bits will help you to improve any kind of data missing by using that bits. That's a very simple question. They do it by the matrix, but describing a matrix for that is really hard and in a public presentation. So that's the simplest type of FEC. And instead of sending 1, 0, I'm sending you 3 zeros, and if any errors happen to one of the bits, you can understand there is more zeros than 1, and you can say it should be 0. There's something's wrong here, and fix it. That's a very good option in our systems, but it eats our speed. Because instead of 1 megabit per second, we should, if you want to have 1 megabit, you should transmit 3 megabits per second. 2 megabits per second for backup in this forward error correction. So it eats your throughput, but it's give you a reliable network. So after that, we know data rates don't come from here. They come from this formula. And in AC standard, this improvement take place. And thanks to that, we can have 433.3 megabits per second in a single stream. How we can make it more? One way is using MIMO. By using MIMO, you can use one screen, just like the movie screen, 2 times at a second, and transmit 2 different images at the same time from the same screen, and double the speed. So if we use MIMO 2 by 2, it means we can transmit double more data compared to MIMO 1 by 1. Okay? One of the methods is using 2 different polarities, and it's really good if you are outdoor. But indoor, there is one more way to use that. When you are indoor, the signal bouncing everywhere to reach you. When one signal travels straight away from the access point, it travels and receives to you faster than a signal that bounces to the wall and turn back to you. There is a time difference between these 2 signals. If we can use that difference, we will have spatial multiplexing, and we can use that to transmit one part of message from this way and one part of message from this way, so we can potentially double speed. Okay? So they're old, and we already use these at AC standard. So what next? The wave 2 of AC access points is on the road, and they will equipped with MU-MIMO. What is that? What that MU can help our network, and for sure it's not MUM, it's MU-MIMO. To understand that, we should understand the beamforming, the concept of beamforming. If you have an omni antenna, it will equally transmit the signal to all over the place. Just like here, there's an omni, and all of you will receive the signal. But what happens if we use 2 antennas close together? To see that by your own eyes, there is a simple test. Go to the swimming pool, drop 2 stones at the water at the same time. You will see the waves is going out from you, and when the waves hit each other, you will have 2 types of events. One event is the constructive combination. It means you will have a stronger wave. It's coming out from your radio or your waves on the swimming pool. And one more. Be destructive. What is that? When we have 180 degrees phase difference, what happened to our wave? They will cancel each other. So we have zero power. Okay? Is it useful? Why not? If we use in an antenna system, we can have a higher gain antenna. That's how every flat panel antenna works. They array the elements, and by that array, they have constructive waves and gives you more gain. How we can use it in our daily basis? We can use that to make different patterns if we have a chip that can make that phase difference. You know, if we have two antennas and make different timings for the phase generation, we can use that fact as an advantage in our system. And we can have a beamforming. How it works? We have a client here, we have a client there, and we have two antennas. So when we want to transmit signal to this client, we have to change the phase, and we will have the signal only in that direction. But if we have another client here, it don't receive that signal. So it's good for unicasting and make the clear channel for the transmission for another user. If we use two antennas, we will have these shapes. And if we use three antennas at single equipment, we will have more power and more shapes. It can go up to 8 or whatever that the manufacturer offered to you, but generally speaking, having more antennas, giving you more possibilities to change the wave of your access point. To doing that and how we can do that, how access point can understand who's there, and to see the environment without having any eyes, there's two methods. One method is implicit mode. With this method, the access points just listen to the signals that coming from the clients and just pay attention to the phase difference that coming to the different antennas that it have and record that phase differences as the best mode to transmit signal to that client. Okay? I'm transmitting signal over there to one access point over here. When I transmit the signal, 2 or 3 of antennas of my access point receive the signal with different timing. And my access point can record that and send back signal to me. It's good because there is no special configuration on the client. I see the eyes closing and the blood is going to your stomach. Okay, everybody raise their hand. Raise up. Do that. Make the blood pumping to your heart. Okay, okay. The implicit mode will help you to do what? To generate the beamforming for every type of client that you have. It's okay. But the problem is if we are in a hall and the Tx and Rx of the signal are not equal, the implicit mode don't work very well. And it happens a lot of time. So the implicit mode is useless. We have one more mode, explicit mode. We need client feedback. We need to ask our clients, how's this one? How's that signal? How's that signal? And we need to sync with our client, and clients that we have will aware of what transmission that we are using. That's the explicit mode. But we add some overhead to our network for syncing. And if we have a client is moving, we need to make it more synchronized than the client that stay in one side. So they're built in a standard, but usually most of the equipment don't use that because of the complexity of that. It also gives you better gain because we are double or triple the waves that go generated by access points, and that can give you higher gain of antenna, and that gain can help you provide better performance to your users and more range. It's a good idea. But what is new in AC? The AC standard are going to use that beamforming in MU-MIMO, and it will be a great idea because at the current situation, at the same moment, we can only transmit signal at a single moment to only one user. It's our technology limit. But in MU-MIMO, in a single moment, access point can transmit signal to different users, just like a switch. If you use MU-MIMO, it looks like you are using a 4-port full mesh switch. And it's great, because today everyone using wireless to watching videos, transmitting data, and switching between users can cause a lot of disadvantage to your speed. So if we can use the MU-MIMO, it would be great. But how it works? The system will use beamforming at the same time for multiple users and form the sending signal to cover multiple users like this. One antenna, one combination of antennas will generate a good beam for user 1, the second one for user 2, the third one for user 3, and at the same moment we can transmit 3 signals to 3 users, and it's cut the edge of the wireless technology. It's good. We can make sure in the near future we don't have problem with data transfer combined with video transfer. Okay, how it works? The system works with a steering matrix, and without using a steering matrix, you'll have that constructive wave in front, but when you use that, you will have a directed wave to your specific user. The system learns immediately after setting up what user can receive your signal good and what user cannot receive the signal good, and use that for the beamforming. It used null for that user and use the max for another user to transmit the signal for multiple users at the same time. And that's the concept of the MU-MIMO. Another thing to improve in AC standard, there's only one thing left, and using the higher data rates by using the QAM, higher QAM, for example, 124 QAM. Is it really works? If we switch to 1024 QAM, we will have 24% more speed. But what we have instead, we will have 400% more possibility for happening errors because we are using more symbols. We are using more dots at that image. So in the real situation, you don't make any improvements. You just sending more signals to improve the mistakes of the modulation that you use, and your radio sooner or later will switch to a lower modulation. Let's say we are at the edge of the AC standard and we are at the edge of 5 gigahertz. What's next? The IEEE worry about that and develop the AD standard. And that standard gives us very big room for moving forward. Why? Instead of 80 megahertz channel width, we can use 2.16 gigahertz channel width. It's a big difference. That much big, okay, compared to older standards. We have a bigger channel, and that makes a big difference in throughput. Here we have 20 megahertz, here we have 40 megahertz, here we have 160 megahertz channel width, but here we have 2.16 gigahertz, and it's a big difference. So it's a good news. If you look at the data rates of AD standard, with a simple 64 QAM, with a weird FEC coding rate, we can have 6,756 megabit per second. If one day we use MIMO, we can have 13.6 gigabit per second, and it's a lot bandwidth for home user. So for sure, we don't have any trouble with wireless in the future, so don't worry about that. But we have some limitation in 60 gigahertz. One of the limitation is manufacturing cost, because it needs a very accurate machines to make that chips, and it's not popular yet, and it will be in the near future, maybe in 5 years. And another good and bad news is the 60 gigahertz is a weird band because the resonance of the oxygen is 60 gigahertz, just like what you have in microwave oven, and 2.4 resonance is the water molecules resonance. And when you turn on your microwave oven, that signal goes to making the water hotter. And that's good for making your food warm. But here, when we transmit a signal at the air, the oxygen molecules start resonancing and capture the power. And compared to other frequencies, here is 10 gigahertz, here in 60 gigahertz, we have a big peak for attenuation in kilometer. So no matter how many power we put at the radio side, at the client side, we will have an attenuated signal. It's bad because we cannot transmit signals so far, but it's good because we don't have any interference from the neighbors. So the air will clear that signal and we will have a clear line of transmission. So that's a good news and bad news together. We should wait for products for this standard in the near future. Okay, what happened in 50 years later? I'm not sure if you can find me and tell me you were wrong, but maybe I'm not in the planet anymore, or you. But in the next 50 years, we should look to the science and find what is missing and what will happen potentially in the future. If we look 50 years ago, there's a discussion between Bohr and Einstein. Einstein don't like the quantum mechanics and he really wants to fight with it. But Bohr really happy with that. Einstein said, God, don't play dice, but Bohr said, don't tell me that. It's not your job to tell what God do or not to do. Einstein very upset that moment and go home and said, I should Bohr. Okay? Burp, Bohr. So when he come back with something that he thinks he found that is wrong in quantum theory, and that's the entangled particles and entanglement. He said, okay, based on your formulas, if we have two particles entangled, if we move one of the particles in one galaxy, the entangled particle in the other galaxy move instantly. So, nothing can move faster than light. And it means your formula is wrong. They don't agree at that moment. And the scientist also wants to know the real answer. But after years, in 1970, some scientists come up with a solution to test that theory, and they put that theory in the test. How they test that? Every particle have a quantum state, and that particles, based on how they rotate, they have this direction or that direction. Particle can be one photon, one electron, or whatever. We call it particles. But when they are entangled, always when you measure one particle and it's in an upward direction, the second particle should be in the downward direction. It's too weird, and no one knows why, but it's happened. They implement a test system and transmit the signals. What kind of signals? The electro-optic signals, laser, that generated from single source here to 2 points. The photons was entangled and they fly over long distance. distance between 2 points. Direct distance is 15.3 kilometer. And there, it's a very complicated test. Not very complicated, but you should know the quantum theory. I don't even know that. So they put that on the test, and they see, okay, the particles act what we should expect, and 100% of the test is correct, and they do the test many more times, and they see, yes, the entanglement is real. They don't know why, but it's real. But the result is amazing. The speeds of that, based on the test equipment that they have, was 10,000 times faster than speed of light. What is that? 10,000 times faster. It happened in the accuracy of test is 3 nanoseconds, and it needs 17 milliseconds for light to travel this distance, but it happened instantly, and they calculate the speed of entanglement is higher than 10,000 times faster than light. So we can only witness this event at that moment, or maybe they can change that and they use this fact in some military equipment and they don't tell us. But if we can control the quantum state of the particles, we can use them for data transmission. And based on what she told me, you will see this in 50 years later. You can communicate from Earth to Mars with this speed in 0 millisecond delay, and MikroTik change to this, rotating the planets. Thanks for watching. Time for questions. Tell me if you have any questions.